Here you see the next AD converter design, which uses the dual slope conversion technique. Many of the problems encountered with the single slope integrator are corrected with the dual slope integrator design. The principal sections of the dual slope integrator converter are the integrator section, the comparator section, the main gate with its clock input, the counter section and output latch, the control logic section, the negative reference voltage or current source, and input switch S1, which is controlled by the control logic section. Also notice that the positive analog input is fed into switch 1 along with the negative reference voltage. When the start of conversion pulse is received by the control logic section, several things occur. 1. Switch 2 momentarily closes to discharge any residue voltage on capacitor C1. 2. A reset pulse is applied to the counter section to ensure that its starting state is 0. And 3. Switch S1 is connected to the analog in input. Notice that all these occurred at the same instant. When the positive analog input signal is applied, the output of the integrator section will ramp in a negative direction. This negative voltage will force the output of the comparator section high. The high output from the comparator section and the series of high clock pulses cause the main gate to produce a series of clock pulses into the counter circuit. This in turn causes the counter to increment. The counter is allowed to overflow and produce a carry signal, which is then applied to the control logic section. When the overflow occurs, the control logic section switches the integrator input switch S1 to the negative precision reference source. With the negative reference voltage now being applied to the integrator, its output will ramp back in a positive direction. This allows the integrator capacitor C1 to begin discharging. Because the reference voltage has a constant level, the slope of the discharge will remain constant, yet proportional to the analog input signal. After the overflow pulse, the counter begins a new series of counts. The counter will continue to increment until capacitor C1 has discharged and the integrator output drops to 0. When the integrator output reaches 0, the comparator output will go low, thereby shutting off the clock pulses to the counter. The count accumulated during this second series of counts will represent the instantaneous input voltage. After a predetermined amount of time, the control logic section will issue an end of conversion pulse to acknowledge that the data at the output is valid. In an effort to simplify the sequence of the dual slope integrator design, we will use this simple timing diagram. The first thing you should notice about this diagram is that the sampled input has a fixed time frame. You should also notice that the reference voltage has a fixed time frame as well. Here you see a low input signal being sampled. When the sampled signal reaches 0 in the fixed reference time frame, the clock pulses going into the counter section stop, which causes the counter to stop counting. The count accumulated during the fixed reference time frame will represent the sampled input voltage. Now you see a larger input signal being sampled. Notice that the sampled signal took longer to reach 0 than did the previous signal. The longer the signal takes to reach 0, the more clock pulses are fed into the counter circuit. The major disadvantage of the dual slope converter is the extended period of time required to make a conversion. The dual slope converter may require more than 50 milliseconds to translate a high input voltage. Next, we shall examine the parallel analog to digital converter design. Very few analog to digital converter circuits are as fast as the parallel converter. The conversion speed of this converter is so fast, it is often called a flash converter. The flash converter uses a bank of parallel comparators to process the analog input signal. One input from each comparator in the stack is connected directly to the analog input signal. The other comparator inputs are biased by a DC reference source through a simple precision resistor network. The resistor values are chosen so that each comparator is biased one least significant bit higher than the next one down in the chain. The maximum input voltage, which can be converted, will depend upon the value of the reference voltage used. Since the output of each comparator is either on or off, they become compatible with digital logic. With no input voltages, the output of each comparator is a logic low. As the input voltage increases, the output of each comparator, starting with the least significant bit, will cascade high as the input exceeds each reference voltage set by the voltage divider network. A network of digital gates which form a decoder network is used to convert the array of comparator signals into a binary word, which is made available at the converter output. As you may have noticed, it takes 2n-1 comparators to support the resolution of this converter. As you can see, this simple 2-bit converter requires 2 to the second power minus 1, or 3 comparators, to support the 2-bit output. An 8-bit flash converter would require 255 comparators, and so on. The vast complexity of this design is one of the flash converter's biggest disadvantages. The major advantage of this converter is, of course, its speed. Since the analog input signal is applied to every comparator simultaneously, the conversion time is basically equal to the propagation delay of the comparators and the gating circuitry. Flash conversion can be accomplished in just a few microseconds. Next, we shall examine the successive approximation analog to digital converter. Of all the techniques that have been covered to this point, the successive approximation approach has become the technique of choice for the analog to digital converter. This is due to its low cost, moderate resolution, and high speed. The successive approximation converter operates by making several successive trials comparing the analog input voltage with a reference signal generated by an internal digital to analog converter. To simplify the operation of the successive approximation technique, we will first examine it in an analogy form using this simple balancing scale system. Notice that the weights are calibrated in powers of 2. There is a 1 ounce, 2 ounce, 4 ounce, and 8 ounce weight. We will begin by placing an unknown weight value on the scale. This unknown value will represent the analog input signal. When the trial weights match the unknown weight, the scale will become balanced. We will begin the measurement by placing the heaviest trial weight in the left-hand pan. If the trial weight is greater than the unknown weight, the balance will shift and the needle will swing left. But if the trial weight is less than the unknown weight value, the scale will remain tilted to the right. In this example, the unknown weight is greater than the heaviest trial weight, therefore the scale remains tilted to the right. Since the scale did not balance, we placed the next heaviest trial weight in the left-hand pan. Notice that the balance of the scale shifted and the scale is now tilted to the left. Since the 4 ounce trial weight weighed too much, it was removed and the next smallest weight was applied. When the weight was removed, the scale would have shifted back to the right, but as you can see, when the 2 ounce trial weight was placed on the left-hand pan, the scale almost became balanced. To finish balancing the scale, we simply added the final and smallest of the trial weights. Once the scale became balanced, we simply added the total trial weight values to determine the unknown weight value. As you can see, the unknown weight value is 11 ounces. This same technique is used in the successive approximation approach when converting analog information into digital information. Here you see a block diagram of a successive approximation analog to digital converter. As you shall soon see, this converter circuit operates by making several successive trials comparing the analog input voltage with a reference voltage generated by a digital to analog converter contained within the device. This circuit consists of a comparator, a successive approximation register, a digital to analog converter, and an output latch. The conversion cycle begins when an analog input signal is applied to the converter along with the start of conversion pulse, labeled SOC, at the successive approximation register. The start of conversion pulse also resets the successive approximation register to all zeros. When the clock signal, which is fed into the successive approximation register, goes high, it turns on the most significant bit output. This in turn sets the output of the digital to analog converter section to 50% of its full-scale output. The successive approximation register then looks at the comparator's output to see if the DA converter reference voltage output is greater or less than the analog input signal. If the reference voltage is greater than the analog input, the comparator output will be off. The successive approximation register will turn off the most significant bit and call it a 0. Or if, on the other hand, the DA converter reference voltage is less than the analog input voltage, the comparator will remain on, and the successive approximation register will leave the most significant bit on and call it a 1. All of this is accomplished in one clock cycle. As the next clock pulse goes high, the successive approximation register turns on the second most significant bit and rechecks the results from the comparator. Once again, if the new DA reference signal is greater than the input voltage, the comparator output will be off, which results in the successive approximation register turning off the bit and calling it a 0. Or if the reference signal is less than the analog input signal, then the comparator output will remain on, which results in the bit remaining on. The successive approximation register will examine each bit in this same fashion, from the most significant bit to the least significant bit, until all bits have been examined. Since one bit is examined during each clock pulse, an 8-bit analog to digital converter using this technique will process the conversion in approximately 8 clock pulses. As you can see, after the least significant bit had been evaluated and processed, the successive approximation register sent out an end of conversion pulse which latched the resulting binary word directly to the output. Even though the successive approximation converter operation is more complex than the 3 previous converters examined, it is perhaps the most efficient type of AD converter presently available. As you have seen, this style of converter is capable of extremely fast conversions at high resolutions. When utilizing this technique, 12 bits of resolution can be processed in 10 microseconds or less.